Tom? Okay, yeah, so unsaturated hydrocarbons. When we talked about saturation, that means that it's saturated what? The carbon molecule. What's saturation versus unsaturation, right? When we think of something being saturated, what do we think of it? It's full of, right? So when we have hydrocarbons, we only have hydrogen and carbon. If it says saturated hydrocarbon, it's full of what? Hydrogens, right? And so if there's anything that interferes with the spots that hydrogen can take, then we would say that's an unsaturated compound, right? So if we have a double bond, for example, we form one carbon-carbon bond, and that gets rid of a potential carbon-hydrogen bond, right? So this is an example of something that's unsaturated, and if we look at the saturated version of this, we would have 3 hydrogens on ethane versus only 3 hydrogens on each carbon in ethane versus only 2 on each carbon in ethene, right? And we talked about the naming last time. These fall under a category of alkenes, right? Where we have the E-N-E ending. That implies that there's a double bond there. And so alkenes tend to be more reactive when it's compared to alkanes. This just has to do with the fact that they have that pi orbital, which is what it's called. That electron density there can react with other compounds. So alkenes are a precursor for a lot of plastics. For example, you start with an alkene monomer, you go through some chemical change, and you can synthesize long chain polymers, right? So we talked about carbon's ability to catenate, right, where it likes to form these long chains. Starting with a long chain polymer a single alkene is a way that you can generate these long chain polymers, right? So they also tend to be reactive with light. So if you shine light on alkenes or structures that have double bonds in them, those tend to be colored structures and absorb light, interestingly. So if you, for example, you can make solar cells out of organic material, those usually have what we call conjugated double bond systems that interact with light so that they can absorb light and then produce electricity. You can also carry electricity through alkene structures. So if you have a conjugated double bond network, and I keep saying the word conjugated, so all that means is that you have alternating single and double bonds. What can happen is that you get kind of these transient switching of the double bonds between the single and double bonds. And if you think about it, if you're moving a double bond from here to there, that means the electrons are moving from here to there, right? So electrons are moving across this distance, and if we have a voltage difference across that, you can carry electrons through this system. So you can actually conduct electricity through conjugated double bond systems as well. And so that's why I think, does someone in here have the Z Flip? The phone, right? So a lot of new phones and stuff, they use this technology. Does anyone know why it would be advantageous to have a organic conductor instead of a metallic conductor? You guys know the Z Flip, the Samsung Z Flip? What does it do? It folds, right? The screen folds, and so if you have an organic conductor, they tend to have properties of plastics like flexibility, so they can bend and whatnot. So you can have stuff that bends and still conducts electricity. Metal, on the other hand, if you bend it, it's going to deform and eventually it'll break, right? So this is, more and more common these days. All right, so that's why we care about alkenes. Well, what is an alkene? It's whenever we have a double bond present, that's when we define it as an alkene, and it's the overlap between these p atomic orbitals, right? So in sigma bonds or alkanes, right, a sigma bond was when we had those hybrid orbitals, right, and those that overlap maybe between 2 carbon atoms. And this is direct electron cloud overlap. With double bonds, you have the unpaired p orbital, which is why the trigonal planar carbon atoms are called sp2 hybridized, right? Because they don't have the third p orbital that's hybridized. It stays unhybridized. And if you have electrons, so there, let's say you have your upspin and downspin here, and then on the other side you have the opposite, your downspin, and your upspin like this. If you have electrons in these unpaired p orbitals, they kind of have this lateral overlap, so they're perpendicular to each other, and when they come together to bond, they then share the electrons in the bonding orbital like that. So this is actually what a double bond actually looks like. We talked, a long time ago about how covalent molecules, they bond, through the overlap of their atomic orbitals. Double bonds are the same thing, except it's not a direct overlap between these orbitals that they share. It's this parallel, perpendicular to the single bond overlap that we get. And this also affects the structure of alkenes quite a bit, because if we had two carbon atoms here, for example, the fact that you have overlap above and below, you can think of it as if you had two carbon atoms with strings going up, and sticks going up, and they had a string tying the two sticks together. So if you had a carbon atom, they have two sticks going up like this, and then you have a string tying them at the top, right? So this represents the double bond overlap, and so that restricts the rotation of it, right? If you have a string there, you're not going to be able to rotate it because it's preventing rotation. So single bonds have free rotation, and double bonds restrict rotation a lot. And then if we get in even farther into triple bonds, all a triple bond is this is one unhybridized p orbital. A triple bond is going to have something where you have the p orbital that goes in the other perpendicular direction, and then those can overlap as well when they form the triple bond. So you get overlap here as well, right? So, and that's why triple bonds are characterized as sp hybridized, right? Because they only have two hybrid orbitals, which form the single bonds around them, and the two unhybridized p orbitals, which form both of the pi bonds, which is what these are called. These are called pi bonds. They form the pi bonds, which form the double and triple bonds for the atom. Okay, so that's a little bit of how the double bonding works. I'm not going to explicitly test you guys on that, but that's what we've drawn lines between atoms, but this is actually what the bonding orbitals look like. And so we talked a little bit about naming them, so you guys could complete your lab last time. It's the same prefixes as for alkanes. Hey, Joanna. So it's the same prefixes as it is for alkanes. The only difference is the suffix changes from -ane to -ene, right? Changes from -ane to -ene because that indicates that we have at least one double bond in the structure. And kind of the breakdown when we have an alkene is you have the number for the location of double bond and a dash, the prefix that indicates, what does the prefix indicate again? The number of carbon atoms in the parent chain, right? Number of carbon, and then the suffix is just plus -ene. If you look up some complicated molecules, you will see variations on this. Sometimes you'll see this number in between the prefix and the suffix, and the dash separating it, and that's when we start to get to really complicated molecules. We have mixed functional groups and stuff in there, and so that's why we started having to take those cases into account. Right, and we always want to place the number of the double bond, which is where the number of the carbon where the double bond starts at the lowest possible number, right? So that has the highest priority when we're numbering our parent chain. All right, so we had that, and so for example, we did this example yesterday where we first we drew the carbon skeleton because I feel like it's a little easier to name the carbon skeleton than it is to look at the Lewis structure and name it. We have 5 carbon atoms in our parent chain, which means the prefix was pent, right? We have a double bond, so the suffix is going to be -ene. On the 4th carbon, right, we numbered it from left to right here because the double bond starts on carbon 2. If we numbered it the other way, we would have the double bond start on carbon 3, which is why we number it from left to right instead of right to left here. And then on the 4th carbon, we have a methyl group, right? So we indicate the position of the methyl group. We separate the numbers and letters with a dash, the name of the group, and then we put another number to indicate, what does this number here indicate again? This indicates the location of the double bond. Right, so that was the example we went over last time for alkenes. Okay, so we already did this one. So why don't you guys take a second and then try and naming this structure. Right, so we have 1, 2, 3, 4, 5, 6 total carbons and 1 double bond. So how would you, in comparing this structure to the last one, how would you compare it? What would you call them? How are they related to each other? I'll let you guys draw it first, but if this was the previous structure, right? Think about how that structure and this structure are related to each other. All right, so I'm gonna draw the carbon skeleton for this. How many carbons are in the parent chain for this? 1, 2, 3, 4, 5. 5, right? So there's 5. So it's gonna look a lot like this molecule, right? So that's how 5 carbon atoms look here. This is what the carbon skeleton looks like. And then which way am I gonna number it? Am I gonna number from left to right or right to left? So I've numbered it from right to left here, but what's the correct way to number it? 1, 2, 3, 4, 5. It should be from left to right, right? Because this puts what at a lower number? The double bond, right? It puts the double bond at a lower number. So double bond is gonna go there. And then what goes on the third carbon? A CH3, which is what group? Methyl group, right? So this is the methyl group. So you can put the methyl group going down here. So how would these two structures be related to each other then? They would be isomers, right? And they'd be structural isomers. Why? Because they have the same number of carbon atoms and the same number of hydrogen atoms. They just have different connectivity, right? Here, this carbon atom has 0 hydrogens bonded to it. In this structure, it has 1 hydrogen bonded to it, right? So we've just moved a alkyl group and a carbon atom, or an alkyl group and a hydrogen, and that generates a structural isomer, right? So we have the same chemical formula, but a different connectivity for these atoms, right? And so the longest chain, we already said, was 1, 2, 3, 4, 5, which means that the prefix for this molecule is what? Pent. Right, so this is going to be pent. And then what's the suffix going to be? Ene, right? Right, because why? There's a double bond there. And what has to go in front of pentene here? Yeah, we'll put the group there too, but before that, what goes, like right before the pentene here? A dash, right? Because we separate the numbers and letters, and what's this dash going to represent? What's this position going to be? It'll be a 2 because it's the location of where the double bond starts. Then we put another dash, and then we'll put the carbon the alkyl group that goes here. And what's the group again? Methyl. And what number was the group on? 3. So we have to do the same thing. It'll be 3 methyl 2 pentene. All right, so again, this is our side group. This is the location of double bond. This indicates that we have a double bond. And then this tells us that we have 5 carbons in parent chain. All right. So everyone clear on that? Make sense? Thumbs up, thumbs to side, thumbs down. Okay. All right. All right, so why don't you guys take a second, take 2 minutes, and see if you can draw the structure for 3-ethyl 2-pentene. All right, so how many carbons are in the parent chain here? How many? 5, right? Because pent, so that means 5 carbons. So I'm going to draw the 5 carbons again. And then we have a double bond because it says ene, and where's that double bond? It's on the second carbon. And then what else do we have on the structure? An ethyl group, and the ethyl group's on which carbon? 3. So 1, 2, 3, 4, 5. This is going to look exactly like the same structure, except it's an ethyl group, and what's an ethyl group? 2 carbon group, right? So this is going to be like that, right? So this is going to be the structure for 3-ethyl 2-pentene. Previous one, we're given the structure, write the name. Here, we're going the opposite direction. Here's the name, write the structure. Okay. All right, so we talked about this a little bit already when we talked about isomers. So alkenes have unique isomers that have the same connectivity but different spatial arrangement. What was the name for this type of isomer? It was if they have the same connectivity and the same chemical formula, but just different 3D spatial arrangement, what did that mean? They were, Yeah, they were stereoisomers. And specifically, these ones for alkenes are called geometric stereoisomers. Right? And what were the 2 types for alkenes for the isomers? Right, this is the one where you had the groups on the same side of the double bond or on opposite sides of the double bond. They were called cis and trans isomers, right? It was cis and trans. If we have a double bond, let's say we have butene, 2-butene, we can have the carbon groups either going in the same direction, across the double bond, or they can go in opposite directions here. Right, so here's the double bond, the carbon group is either going down here and up here. That would be trans, because they're on opposite sides across the double bond, or a cis isomer is going to have them going on the same side across the double bond. That's it. Because they have the same connectivity, right? If we look at this carbon atom right here, right? This carbon atom is bonded to 1 carbon atom, 2 carbon atoms, and then there's a hydrogen going there too, right? The hydrogen is implied. If we look at this structure, it's the exact same thing. This carbon atom is bonded to 1 carbon atom, 2 carbon atoms, and hydrogen. So it's actually bonded to the 3 same elements, and it's bonded in the same way to them. The only difference is that the shape of these molecules is different, right? So they're distinguishable from each other, but they have the exact same connectivity. If we had, for example, using the same structure, now that would be a structural isomer, because we have this carbon atom is bonded to 1, 2, 3 carbon atoms, and this carbon atom is bonded to 1, 2 hydrogens, right? So the actual connectivity for them is different from each other. And this is why you need 4 unique groups on the sp3 carbons to get chiral centers and stuff, is because that's the only way you can have the mirror images, non-superimposable mirror images of each other. The connectivity is the same, meaning the same atoms are bonded to the same atoms, but the way they're arranged in 3D space is very different. So for example, in trans fatty acids, for example, you'll have these trans double bonds throughout the fatty acid side chain versus cis double bonds. And that, you can imagine, changes the shape of what a long side chain would look like, right? The double bonds, since they're not allowed to rotate, right, it restricts them to the plane of the double bond right there for the sp2 carbons. It makes it so the structure is restricted in a lot of ways. So it can add bends and whatnot to a structure, even though the connectivity is the same, and that changes the physical properties a lot. So for example, saturated versus unsaturated fatty acids have very different melting points because of that. Okay, we're not going to do that, blah, 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 polyacetylene. So this would be an example of a polymer, right? So this goes on, indefinitely for very, very long side chains. What would be the configuration of the double bonds in the first polymer drawn here? yeah, these would be a trans configuration. And how do you know it's a trans configuration? Well, if we follow the double bond, right? This is the double bond right here. We have one group below here, and then one group above the double bond there. Then we go to the next bond, one group below, and one group above, right? So we're across the double bond. Groups are on opposite sides of the double bond. Here, in the bottom, we have the cis configuration, right? Because the groups are on the same side of the double bond. So that would be trans polyacetylene, and this would be cis polyacetylene. Okay, does that make sense? Does everyone see how these are trans and cis, or how trans and cis isomers work with double bonds? If you're naming a structure with a trans or cis isomer, the only way the name changes, you just put trans or cis in front of the isomer. I won't ask you to name the trans or cis isomer. I'll just ask you, is this a trans or a cis isomer? Polyacetylene. I wouldn't worry about drawing, because these are long polymer structures. Really, you only need to draw one repeat unit for this. And then you can also have these trans and cis isomers for ring structures, because remember last time we talked a little bit, if you have a closed ring and a alkene, those tend to be isomers of each other. The top one? Or, okay, yeah, so here's the double bond, right? And we have the group, right? The two groups are going across the double bond, right? So if we rotate our frame of reference, kind of just tilt your head to the side 30 degrees, you see how that looks similar to this right here, right? If we rotate this, that kind of looks similar to what the double bond looked like when we define trans and cis, right? Then, if we look here, these are the R groups. They're both going in the same direction across the double bond. They're alternating above and below, but they're still cis configurations for that double bond. Yeah, it'll be like this, exactly right. The only thing that'll change is that these groups across the double bond can change. So for example, we could have something like this and something like that. That would still be considered a trans configuration, but now the different groups. So what kind of group going up on the right here? Tert-butyl, right? That's our tert-butyl group. And then below we have, how many carbon atoms are in that group? 3, so that would be isopropyl, right? That's our isopropyl. And we actually wouldn't name this like that at all. We would name it 1, 2, 3, 4, 5, 6. And on this molecule, we have how many methyl groups? 3 methyl groups, right? We have, oops, get rid of that. 1, 2, 3 methyl groups attached to the parent chain. You could number it like this, like this, or you can number it that way. It doesn't matter. It'll give you the exact same answer. And then we have a double bond, right? So how would we name this? We would name this. This would put at the lowest possible number. We can name it left to the right or right to left. It doesn't matter. We could put 2, 5, 5. What would be the prefix for if there's 3 methyl groups? The prefix in front of the substituent group. Right, we have 3 methyl groups, right? These are the location of all the methyl groups in our molecule. What would the prefix be for 3 methyl groups? When there's 2 methyl groups, what do you say? We say tri, right? Trimethyl, right? Tert-butyl is its own specific group. Trimethyl, it was what we would say for having 3 methyl groups. So this would be trimethyl. Prop is for when we have 3 carbon atoms in the group or on the parent chain. So trimethyl, and then we have another dash to say the location of the double bond, which would be 3, and then there's 6 carbon atoms, so what should the prefix for the parent chain be? Hex, and then ene because there's a double bond. So last time we were like, well, why do we have to put 5 twice here? Well, because we have to indicate the location of all the different methyl groups here. And there's 3 methyl groups on here, even though really what we're looking at is an isopropyl group on a double bond and a terp-butyl group going up from a double bond. The way you name it according to the IUPAC convention would be something like this. And you'll get familiar with, you're saying, oh, this is named in this way according to these rules, then you'll see what they actually call it, and a lot of organic molecules have common names. So a lot of carboxylic acids, for example, are almost all entirely common names because those were discovered way before the naming convention was invented. Okay, so that's just an example of how we would name a structure like this. This is a little complicated. I don't know if I'd give this to you guys because he put me in a bad mood or something. And then we also have cis-trans isomers for cyclic molecules. And I'm never really gonna test you guys on this. I just want to introduce it. So here we have 2 ring structures, right? So remember, double bonds and ring structures, alkenes and ring structures. Let me go back. What's that?
There's not like a trans thing.
Yeah. So if you were to indicate the type of double bond here, how you would name this would be trans 2,2,5,5 trimethyl hexene, trimethyl 3-hexene. So if you were to indicate that, I'm not going to ask you guys to name the isomer of it. I'll only ask you what is this isomer. So don't worry about it unless you're specifically asked about it. Okay, and yeah, so then for the ring structures, remember alkenes, right? If we have a butene molecule like this is a structural isomer with cyclobutane, right? Because when we take the edges and we put them together, we get rid of 2 carbon atoms to form a carbon-carbon bond. It's the same thing when we form a double bond, we get rid of 2 hydrogen atoms to form the extra carbon-carbon bond. And so these are structural isomers with each other, and because of the geometry of rings, we can have cis and trans configurations here. So this would be the ring, right? This is a 3-member ring, so what's the prefix for it? It's cyclo, right? So it's cyclo, and then it has 3 carbons, so it would be prop, right? So this is when the number of, right? I know it's gonna get confusing. We're doing the prefixes for the number of side groups, and then also the prefix that tells us the number of carbons in the parent chain. So there's so this cyclopropane is the ring, and we see that this can have both of the groups going above the ring, or it can have 1 group above and 1 group below, right? So these would be the 2 cis-trans isomers for the ring structure. And so like I said, I'm not really going to test you on this, but this is also where we see that. And that's because cyclic molecules are structural isomers with alkenes. All right, so we'll finish. So after this, all we have is the reactions of alkenes, and then we'll talk about alkynes, which is just when you add a triple bond. A triple bond, you'll see the structure just on quizzes and exams and stuff, but really it's the exact same thing as how we deal with double bonds. We have we don't have cis or trans isomers, but it's just the prefix, the naming, that all of that's exactly the same, except the suffix for the molecule is going to be YNE. All right, so we'll stop there for today. We'll finish this up on Tuesday, and then we'll get into more complicated functional groups.